Hello everyone. Today I'll be presenting Lab 3 for Physics 2211. Our objective in this lab is to estimate the mass of an unknown black hole by analyzing the motion of a star orbiting it. To do this, we're given the following information: that the star has a mass of 2.0 times 10 to the 30 kilograms, and the black hole is positioned at the origin. We also receive a data set containing the star's position over time. Our approach is straightforward. We assume that the only force acting on the star is gravity from the black hole. We then use a time step of 1 Earth day to compute the net force exerted on the star. Using this, we can estimate the black hole's mass by averaging multiple calculations. So as for the equations, to estimate the mass of the black holes, we rely on key physics equations. First, we use Newton's law of gravitation to tell us the force between two masses is proportional to their product and inversely proportional to the square of the distance between them. Next, Newton's second law states that net force on an object is equal to its mass times acceleration. We also use update equations to determine the velocity and position of the star at each time step. The velocity update formula helps us calculate changes in speed, while the position update formula determines how the star moves over time. Finally, we break the force into parallel and perpendicular components. The parallel component affects the star's speed, while the perpendicular component influences direction, curving the orbit. Now, looking at the equations in our code, first we define the necessary constraints, including the gravitational constant, the mass of the star, and our time step. Next, we compute the gravitational force acting on the star by using Newton's law of gravitation. We then update the star's velocity and position using the update equations from the previous slide, and then we finally calculate the estimated mass of the black hole based on our computed forces and distances. As for our output, once we run the code, we obtain the star's trajectory and an estimation of a black hole's mass. Specifically, by analyzing the motion of the star, we can see how gravity affects its orbit. Our mass should be close to its theoretical values, which demonstrates that our approach works. However, there may be slight variations due to numerical errors, which we'll discuss later. So now we're going to introduce a second scenario. So in this case, the planet remains fixed at the origin while the moon orbits around it. The spaceship starts on the moon and must navigate a figure-8 path around both the moon and planet without crashing. Our goal is to find an initial velocity for the spaceship that allows for it to complete this orbit while responding to gravitational forces from both celestial bodies. So the code for the spaceship simulation is pretty simple. To model the simulation, we begin by defining the masses and initial conditions for the planet, moon, and spaceship. The moon's orbital speed is computed based on its distance from the planet. We then assign an initial velocity to the spaceship that allows it to interact with both the planet and the moon. And next, we update the spaceship's position and velocity using Newton's laws, similar to how we did for the star in the previous scenario. So when we run the simulation, we observe how the spaceship moves in response to gravitational forces. If the initial velocity is set correctly, then the spaceship follows a stable figure-8 path around both the planet and moon. And if the velocity is too high or too low, the spaceship might either escape or crash. This highlights how sensitive orbital motion is to initial conditions. So what does this mean? Let's break this down into what this tells us about motion and forces. First, we see that every object in our system is influenced by gravitational forces. We also see that momentum changes over time following Newton's second law. The parallel force component alters an object's speed, while the perpendicular component curves its trajectory. The key takeaway is that accurate force calculations are essential for predicting motion in any gravitational system. As for what if, in reality, every object in space interacts with every other object. While the black hole has the strongest influence, smaller bodies like the planet, moon, and spaceship still affect each other. To model a more complex system, we would need to account for all gravitational interactions and continuously update each object's position based on the combined force of gravity acting on it. So for some potential sources of error, the three main things I want to know is breaking the motion into steps, uncertainty in initial conditions, and the limits of computational precision, as you can see here. So in conclusion, in the first scenario, we estimated the mass of a black hole by studying the orbit of a star. In the second scenario, we simulated the motion of a spaceship navigating a figure-8 orbit around a planet and a moon, and these models demonstrate how physics and programming can be combined in order to study celestial motion. Thank you for listening.